Hi, everyone. Welcome to another week of lectures in climate data science. Today we'll be having our internal research progress presentation from Qingyuan Yan and Hongseok Yu. We'll start with Dr. Yang with his presentation, emulating and analyzing two climate model perturbed parameter ensembles, PPEs, using a simplified additive Gaussian process emulator. Dr. Yang is a postdoctoral researcher at LEAP, where he works on developing and applying different machine learning algorithms for the emulation and parameter estimation of climate models. He previously worked as a research fellow at Nanyang Technological University and received his PhD and master's degrees from University of Buffalo, SUNY, and bachelor's degree from Nanjing University. Welcome.
Okay, first of all, thank you for your time joining this presentation. So I want to introduce you guys emulator method that does emulation and analysis for climate model PPEs. So we know that PPEs are generated so that we can study the relationship between the parameters and model outputs. And they can be used to further to train the emulator and then used for parameter estimation. So PPEs are increasingly being developed and widely used. So we think it's kind of important to present something that's comparable and does analysis to look at the PPEs. So what we meant is that we want to be able to not only emulate the data, but also know what we're emulating in the data set. So this is kind of the idea of this work. And also there are some limitations in the more traditional ways to look at the PPE data set. So correlation between parameters and outputs could be underestimated because it's just somewhat linear. And also if we use sensitivity tests based on data generated from the emulators, the emulator are imperfect. So it might have errors. It may or may not affect how we interpret the results. And we don't know why and which methods are best to work with PPEs with very few ensembles, which is very common. So in this work, we're introducing this method, apply the method to two PPEs, compare its performance with neural network, and more importantly, to see if we have some insights from this work. And our target variables are just different kind of climatologies, but they are model scores. So they are kind of like a squared error, absolute difference between the model output and observations. So the key idea is that this method is like extremely simplified from the additive Gaussian process. So like the reason we came up with this is actually the fact that the PPEs are very sparse. So normally we have the ensembles, we only have a few hundreds, but the parameter space is several tens. In this case, it's 45. So it's very sparse. So we think there might be complex structures in the data set, but they cannot be preserved. So why don't we just focus on the simpler ones? So we aim at emulating this, I call it low frequency variability. An example is shown on the right. So given a signal, we're not focusing on the zigzag sine waves. We're only focusing on kind of the long wavelength signals in the data set. So there are lots of simplifications, as I said, and we made it clear that so this method doesn't estimate the uncertainty, which is for now a limitation. So we decompose our target variable into additive terms, and each term is the mean of a Gaussian process that only takes 1, 2, or 3 parameters as input. And also we fixed the hyperparameters of these Gaussian processes. So this might seem a little bit odd, but if we keep the Gaussian, so we can kind of control it by fixing it. We're only emulating kind of the, sorry. It's a bit, so we're only emulating kind of this long wavelength variability. This sensitivity will be tested later. So sorry for this back and forth. So this is how the method works on a practical level. So it first focuses on the one parameter Gaussian processes. It builds one parameter Gaussian process for all the parameters as shown on the right. and it picks the parameter that gives you the least root mean square error. So that's the parameter for this iteration. You fit it, so you can see this red line here, and you pass the residuals from this emulator to the next and do the same thing, identify a series of parameters. After these are done for the one parameter processes, we move on to the two, like parameter pairs. It's exactly the same way, except that we're using a different measure. So this measure is showing like the additional benefit of emulating the residuals from the previous iteration jointly compared to emulating them independently. So here's the kind of the grid file is an example. So the x and y axis are both the parameters. So the triangular grids here is showing like all the possible pairs, and some of them will.
Sorry, can you say more about what the parameters are?
Oh, the parameters are just from atmospheric models. Yeah, is that okay?
Yeah.
Yeah, okay. So some of them you can see the red really stands out. So you pick them and you model them, you do it sequentially. So since the method is additive, it's very easy to monitor how the performance improves. So the y-axis is kind of the residuals you have after each term is added to the emulator prediction. So you can see the first term, the DCS here, adding that adds to a great explanation to the data, and it gradually decreases. It's very gradual. And there are three bars like at the bottom of the figure. So the first bar corresponds to all the terms that are single, corresponds to individual parameters, and the other two are kind of parameter pairs and parameter groups of three. So they do contribute to explaining or to the emulator performance. So sorry, this is very sensitive. We're applying this method and the neural network to two different PPEs. Their main difference is that they have different number of ensembles. One is 750-ish, the other is 260. So we are doing 80% for training, 20% for validation, and here is the results denoted using R squares. So the comparison is on the left, x-axis neural network, y-axis this method. So the bars are showing kind of the variability in the R squares due to sampling. So I would say that the performance of the two methods are pretty comparable, especially for the ones with greater R squares. There are some that are not great, which are marked in green. So in this case, it's to the right. So neural network works better. And I want to point out this single variable TIWP is the total ice water path. So that's the amount of ice in the cloud. Somehow, our method just really outperforms in emulating this single variable, and we'll see why later. Figure on the right is it's showing the R square variability from using the same R method. The y-axis is from the random sampling, which is basically what the y-axis on the left shows, and the x-axis is showing the variability of the R square by varying the hyperparameter. So it's very small, so which we're happy about. So it's the hyperparameters. If we're focusing on the trend, these hyperparameters doesn't really matter that much. We did the same. I apologize for this. We did the same thing for the CAM6 PPE. So it has fewer ensemble members. So it's not that surprising the performance of the method deteriorates a lot. And in this case, we think that our method works slightly better than the neural network. So you can see some more points that are to the upper right. So that's a good sign. Sometimes with neural network, it even has negative R squares. So in that case, the emulator did nothing but introduces additional errors to the prediction. So it's a bit strange, but it happens sometimes. And again, the same thing on the right. So it's showing that the hyperparameters doesn't really matter that much. So this figure looks a bit messy, but basically summarizes the contribution of each individual parameter here on the right, and the contribution of the parameter groups. So the colors of the points here is basically the difference of each point in this figure. So to save you some time looking at this messy figure, So we notice that there's a few parameters that contribute individually greatly to the overall emulator performance. So that is the DCS. So you see lots of red points there. And also on the right pane, these are all parameter pair or groups contributions. So they also play a role. So we cannot ignore the contribution of parameter pairs. And this figure also explains why the parameter, we emulate the variable TIWP very good, because the parameter, there's only this parameter, I think you can see on my mouse here. There's only this only one parameter VF mod S. That's the only single parameter that contributes to this parameter. So our method looks at the variable one at a time. But for neural network, it cares more about the overall performance of the method. So this improvement in this single variable is somewhat neglected by neural network. And we think this is important because for all kinds of PPEs, there might be such variables exist. And we know that and be aware of it, that might lead to better emulator performance. So again, this is too messy, so we organize it furthermore. So here's an example. So we grouped them based on their contribution to the RMSE decrease. So the individual parameters, so what I'm showing now is the y-axis is the colors here. So you can see there are some parameters that obviously are important, but there are some that are kind of below 0.05. So we group and sum them together to see what are actually contributing to the emulator performance, and here is the results. Again, the y-axis are the variables, and the x-axis are like how it's categorized. So again, trying to summarize it, the contribution from parameter groups is not negligible. So in this figure, these contributions are the like lighter, brighter colored bars, the yellow, orange, and red. And also we note that a group of single parameters that may seem unimportant. So these are the light blue bars here. They may seem unimportant individually, but since our method is additive, so altogether, they could have a very non-negligible cumulative effect on the emulator performance. So we think this is important because if we saw some results like this, we would say, oh, for the blue bars, there's maybe only 2 or 3 parameters that matter. But from this analysis, it seems that all these very low bars are equally important when they are combined together. So so we're focusing on the PPEs with more ensembles here. So remember that there are some green points that do not perform as well. So we think, oh, maybe because our method looks at variable one at a time. So the relationships between the variables is kind of ignored. So we say, oh, why don't we just predict easy to predict variables and put them together and make a new emulator focusing on these difficult variables. So that's what we did, and figure on the right is showing the improvement. So the green points are the performance before compared to neural network, and you see that the yellow points are the update. So there's only one exception with no improvement in the emulator performance. All the others are pretty well and comparable to the performance of the neural network. So this is more like a deep dive into why including these easy variables work. But I think I'm kind of short in time, so I'll just pass it later. So now we're moving on to the CAM6 PPEs. We want to know kind of why the method, in this case, outperforms neural network, although overall, none of them work extremely well. So we think it's probably the main reason is similar to why our method works well with TIWP. So for all the variables, there are some variables that are just somehow really difficult to emulate regardless. And because neural network focuses on the overall performances, these really bad variables, trying to emulate them very hard for the neural network would kind of drag the performance of the neural network for the variables that are easier to predict. We think that is why. And again, I'm showing how the contribution of different parameters, just like shown before for the other PPEs. And please note the gray bars, this is the variability from the random sampling. So in this case, it's very different from previous results. So only the dark blue bars is kind of robust. So you can see the variability of the gray bars is comparable to the contribution of those parameters that contribute less to the data set. So it's probably a matter of ensemble size. So figure on the left you've seen before, that's the CAN PPE results. So we have the model E PPEs with more ensembles. So we say, let's just train 250, let's just train the data with 250 points, and here is the result. And when given fewer training data set, you see the performance of our method is very comparable to neural network. And interestingly, some of the performance is actually more robust. So you see fewer variability for using our method. Again, this is because with fewer samples, the neural network may only try to memorize it and not trying to, so it overfit a lot and not trying to kind of predict the pattern. So as I mentioned before, we're trying to emulate the model score. So it's absolute difference between the prediction and observation. So because of the absolute difference, that kind of folding or compressing some useful information. So instead, we're emulating the raw model output at different latitudes. We select 4 variables for the test, and the y-axis is again the r², and the x-axis are the selected latitudes. The blue lines are the r² from emulating those scores that we showed previously. So first of all, you see there's a big improvement for some of the variables, and also you see the difficulty in emulating these variables varies at different latitude, which we think is really interesting, and we want to delve into it. And there, of course, there are other factors affecting how our emulator performance. That's kind of ongoing. So to summarize, we're presenting a new method. We apply it to two different PPEs, and its performance is comparable to neural network. And we gain lots of insights that might be universal for other PPEs and for other emulator methods. So I'm just listing it here to save some time. And at the end, I want to do an advertisement, which is please join the parameter estimation focus group. It's very informal, but it's always very informative, and I learned a lot from that. So thank you.
Do we have any questions in the room? And if you are online and have any questions, feel free to we can start with Linnea online. Can you unmute yourself?
I can, yes. Thanks, Young. I'm interested in if you compared the results of your sensitivity test with the additive Gaussian processes to like a more traditional sensitivity test with the neural network. You had mentioned that you're worried that the network is there's someone in it and you'll get different sensitivities, but I'm curious if you found that your method is drawing out things that were missed.
I'm not sure if this answers your question, but yeah, we did. So I was worried that, oh, maybe it's just our method. It's just our method. So what we did is, so you can see here. So the parameters that contribute greatly, so more than 5% of the total standard deviation, there's only about 13 of them. So we train another neural network just using these 13 parameters, and we plot its performance, and they are shown as the crosses in this figure. So you can see a very systematic decrease in the emulator performance. So the crosses are the performance of neural network without the quote unquote insensitive parameters. And the empty blue bar is the performance of the neural network with all the parameters. So we're happy to see there's a big drop. So it's not just from our method. So even for neural network, it decreases and the amount is very comparable. Does that answer your question?
Yeah, that's great. Thank you.
Okay.
Anyone else in the room? there anyone else online?
So yeah, so I was expecting people asking why the Gaussian process wouldn't work. So I just throw a question and answer it myself. So we did that, and turns out neural network slightly outperforms the Gaussian process. So, and yeah, since there's no questions, I can explain a bit more on the hyperparameters. So imagine that we have these black points they're actually the sum of two sine waves. One is high frequency, one is low. So so you can see lots of colored lines in here with very different fixed Gaussian process hyperparameters. So in figure D, you see the blue lines and red lines very similar, but they have very different hyperparameters. So that is what I meant. So if you focus on this very kind of low frequency variability, the hyperparameters don't seem to matter that much.
There was like one more plot where you showed like the feature importance. There was like one plot where you showed feature importance. I think it almost looks like the energy content when you do like SVD or like PCA. So is that like something
You mean like something like this, like kind of decompose is important?
I think
The
it was
previous one?
the one this like it was like an L-shaped hood,
It's like a what?
like an L-shaped.
Yeah, I think we can maybe look at this figure. So
Yeah, like is if you do like say like Sobol indices or like any sort of parameter.
oh yeah. So
you get like something similar with that.
we didn't try it, but if you do the Sobol indices, you need to generate lots of samples from the emulator. So we think that that might, because the emulator are not perfect. So depending on its performance, it may or may not affect how you interpret the results. So by making it very additive, it's very simple, and all these bars are definitely additive under the framework of this.
So like basically like one of the main advantages here is like one of the main advantages here is that it's like much easier or like much more computationally.
Yeah.
Just
Yeah.
okay.
Yeah. Yes.
Any other questions in the room? Or online, you can feel free to mute yourself. I think that's,
Thank you for your time.
thank you.